Okay, so we're going to explain how simple harmonic motion relates to circular motion. So here we have an object moving in a circle. Maybe it's moving from left to right or right to left, doesn't really matter if it's moving clockwise or anti-clockwise. But it's moved through a particular angle in a certain amount of time. We can say that the angle is the angular velocity is that angle divided by the amount of time. So what angle does it move through per second? That would be what the angular velocity is. So, as we know, in our solar system, we have planets orbiting the sun, and we have some of these planets have moons orbiting those planets. The story goes that I think it was Galileo was looking through a telescope, and he saw. Oops. Okay, that's not what I want to do. He saw Jupiter. So let's say I'm just going to draw a little circle here. This can represent Jupiter, and he saw these things coming off to one side, and he sort of he drew sketches of where they were at different points in time. So he'd have a look at them each day, and he'd notice that they would be here, then they would be over there, and then they would be maybe a little bit closer, and so on. It'd be all these different positions like that. And he said they were behaving like springs, like they behave like simple harmonic motion. They behave like a spring would behave. It would just go back and forth like this. And so he was very confused, but he said, well, it seems as if this planet up in space, they would refer to it as the heavens back then probably, had these springs on it that was going back and forth. Now, what the problem was, he was looking, it was all down to perspective. He was looking at the orbit of this moon, or maybe moons, edge on. So if we rotated this, what would actually be happening is the Jupiter, let's put that now in the middle of there, Jupiter would be in the middle, and the moon was going around it like that, but he was only seeing it edge on. So it turns out that if you were to rotate something, move the orbit of something or anything moving in a circle, and if you rotate the circle so you don't see the circle, you see the edge of the circle, you know that we would get this object that is moving in a circle, but it would seem to be going back and forth, like this. Why can't I do it? I can't seem to make it go in a horizontal line. Okay, so it just go back and forth. So that's what he was noticing when he looked at the moons of Jupiter, and he's very confused, and it's because he was looking at the edge on. So we want to try to understand why would it behave like that in that way. So okay, I think I've got that thing going. Hang on a second. Right. Okay. So basically, let's imagine this thing moving in a circle. What would Galileo see, or anybody see, if we're looking at this circular motion edge on? So the person was looking at it like that. That was their line of sight. They're not seeing our vantage point. We're looking at it essentially from above, so we can see the circle. They can't see the circle. They just see the edge. Like you turn a plate on its side, you just see a straight line. So what position would they see it here? Well, and what position would they see it there? Well, there they would see it in the middle, and there they would see it, here. So we're going to try to understand their point of view by drawing this line and then matching it up with where they would see it. So this one, they would clearly see it there, and that one they would see it in the middle. Now, what we've got here is a bit of a trigonometric triangle, because that would be a right angle. This distance here would be what they think the distance is, which we could call x. And that the hypotenuse of the triangle would simply be the radius of the circle. Okay, that angle theta is also that angle up there, because that line is parallel with that line. And so we can use a bit of trigonometry to relate x to r. So let me just pause the video and see if you can work that out. Okay, so we've got x is opposite that angle, r is the radius, well, it's the radius, but it's also the hypotenuse of the triangle. So we can say that theta is, sine theta is equal to opposite over hypotenuse, which is x over r. Let's write that more neatly. So x, therefore, is equal to r sine theta. This is, and we know that because we're moving in a constant velocity, or constant speed around this circle, so constant, if we're moving in a constant angular velocity, then that would mean that that theta, theta is proportional to time. In fact, we can come up with this relationship here. We can say that theta is equal to omega t. So we can sub that in. We can say x is equal to r sine omega t. So this is the relationship here. Now, what we do now when we're looking at simple harmonic motion is we almost imagine there is a circle there. Then we're looking at it edge on. There is no circle, but in any real simple harmonic motion, but we're imagining the circle, and this is why we use omega. So we have this imaginary circle that we use, where if we imagine the beginning point, let's say this is moving clockwise, then when omega is 0, then so when omega is equal to 0 radians, it doesn't matter anyway, 0, then x would be equal to r sine theta, or sine theta of 0, so x is going to be 0, and that's what it looks like because x is at the middle point. When omega is equal to 90 degrees, but that would be, I've got to think about this now, 2 pi is a whole circle, pi is half a circle, so pi over 2. When omega is equal to pi over 2 radians, then x is equal to the maximum point r. So we could just simply think of r as just equal to the amplitude, because it's the maximum point. And so we could rethink the equation here when we come to simple harmonic motion as x is equal to the amplitude. Maybe you could call this xo sine omega t. And then we looked earlier on about how we can differentiate this. So we know when we differentiate sine, we get cos. So dx by dt, which would be velocity would be equal to the maximum velocity multiplied by cos. Oh, actually, I wonder if the relationship's a little bit more complicated than that. Let me just have a quick look. Yeah, I got that wrong, actually. We're going to differentiate it properly, like mathematically. So, so basically you bring out this omega, and you keep the xo, so omega xo, and then that's what the velocity is. And then finally the amplitude, we know is going to be, when you differentiate cos, you get negative sine. We've got to bring out the omega again though, so that's going to be negative omega multiplied by that omega, so omega squared, xo sine omega t. But just remember, the omega is referring to the angle moved through in an imaginary circle. And so, essentially, when at the beginning of an oscillation, we say that omega would be 0 when it's at the middle equilibrium point. Then as it moves all the way around back to the equilibrium point, it's moved through half of a circle, half of a cycle. So that would be pi radians. then a full cycle would be 2 pi radians. So that's how it relates to circular motion.